Hi, it's Kate, and this is the first video for week 13 of Math 23. We made it! Well, this is the first video, so we haven't made it quite yet, but let's get started. We left off 2 weeks ago talking about constrained critical points. Well, we were just talking about critical points in general, but in this particular case, we want to be talking about constrained critical points. So not only are we maximizing a particular function f, but we only care about points of this function that lie on the manifold, and that manifold is our constraint. And so what's interesting is that if we have an actual point that's a local extremum of this function, restricted to the manifold, so that means that this point C happens to live on the manifold, and if you consider the function value of all the points on the manifold, C is going to be a local extremum of the function, then the tangent space at the point C, the tangent space to the manifold at the point C, rather, is part of the kernel of df of C. So it's in the kernel of df of C. We're going to talk more about how to prove that, but there are lots of different ways to describe a manifold. Remember, manifolds are just a general family of smooth curves and surfaces that locally can be described by C1 functions. Right? You might need to use multiple C1 functions depending on which part of the manifold you're on. But we learned 3 different ways to describe a manifold, and so there are going to be 3 different approaches depending on how you've described this manifold to find these critical points, these constrained critical points. The first way was if you describe the manifold as a graph. So near the critical points, the passive variables x are a function g of y of the active variables y. If we define the graph-making function, which is this g tilde here, and it returns just all the passive variables and all the active variables, f composed of g of y specifies values of f only at points on the manifold. And in fact, I want to make a very small correction here. I missed one typo. This should be f of g tilde of y. So what you're doing is you're taking all the actives and the passives, and it doesn't matter, you're not only taking the passive variables and plugging them into f. You're talking about any point that's on the manifold. So within a point, all the components of a point are going to have active and passive variables. So when we talk about the function value of f at a point on the manifold, then that needs to be g tilde, f of g tilde of y. So this specifies values of the function f only at points on the manifold. To search for unconstrained critical points of this function, we set the derivative of this composition equal to 0. So df composed of g tilde is equal to 0. And this approach works really well if you can represent the entire manifold as a single function graph. And you guys have actually already used this approach before in your univariate calculus class when you did optimization problems. Sometimes you were able to put the constraint straight into the function you were trying to optimize. And then you took the derivative and set it equal to 0. So you should be familiar with this general approach. Now, of course, there's another way, which is if you've parametrized the manifold. Now, you have described the manifold as gamma of u. The points of the manifold are specified by that parameterization. So f composed of gamma of u specifies values of f only at points on the manifold. So again, that's sort of like the same as doing f composed of g tilde of y. F composed of gamma of u is the range of all the function values that you could get from points on the manifold. And so to search for critical points, we now want to take the derivative of this composition. So it's df composed of gamma, setting it equal to 0, and solving. And this approach works well if you can parameterize the entire manifold, especially with one parameterization. I mean, with multiple, that's very rare and it kind of gets a little gnarly, but it's doable. Now our last way is our manifold is specified by constraints. Let's take a look. So our manifold is specified by constraints. Our points on the manifold all satisfy the constraints f of x equals 0, right? It's being described as a locus function. And we already know, based on the properties of describing it as a locus function and our proof from last week, that the tangent space at a particular point on the manifold is equal to the kernel of df, that big F, the locus function. So the rule for a critical point, because the tangent space of a critical point is in the kernel of d little f, the function that you're trying to optimize, we now know that, well, the kernel of d big F, where big F is the locus function, is in the kernel of d little f, where f is the function you're trying to optimize. We're going to be working with this a lot more in class and in a lot of our proofs. If there's just a single constraint, big F equals 0, both derivative matrices are just a single row, and you can represent the condition for a critical point as kernel alpha is a subset of kernel beta. So what is that saying? Well, if we have a vector that is an element of kernel alpha and beta equals lambda alpha, the quantity lambda is called a Lagrange multiplier. And so what's interesting is that at this particular critical point, we have d little f acting on v equal to beta v, which is equal to lambda alpha v, which is equal to 0, because v was in the kernel of d little f to begin with. So that is true. This fact is true, that d little f of acting on v is equal to 0 for any vector in the tangent space of big F equals 0. And so we have a constrained critical point. This is really difficult to talk about abstractly without just doing out the proof, and this is actually one of the proofs that we're going to open lecture with, I think. I mean, you're definitely doing it this week, I just don't know whether it's going to open lecture. But so I don't want to go into all the nitty-gritty because I'll basically be doing it for you in advance of your time in class, but it's not quite so obvious that the condition that beta equals lambda alpha has to hold, that it's necessary as well as sufficient. But we will actually be doing this proof full out. You'll be getting all the details and you'll sort of understand how it works, and then you'll get some actual good practice in using this very interesting method called Lagrange multipliers, where you can very easily solve quite complicated constrained optimization problems using pretty straightforward algebra once you've figured out this entire method of setting it up.